Hello everyone, in this video we are going to look at the experiment that we did last week. So last week we were given PPG sensor data and we used DFT Magnitude Spectrum to compute the pulse rate, and we compared the results that we obtained with the ones that we got from autocorrelation function by using the same data. So basically discrete Fourier transform or DFT is the signal that we get when we do sampling of DTFT signal. The discrete Fourier transform x of k of a signal x of n is defined as this thing over here, this image. So x of k is equal to sigma n is equal to 0 to capital N minus 1 x of n into e to the power minus iota 2 pi by n into k. And this cost value is the real coefficient and the sign value is the imaginary coefficient. And the graph of mod of x of k against frequency is known as the magnitude spectrum. Mod of x of k means the magnitude of x at the frequency k. And similarly, the graph of argument of x of k against frequency is known as the phase spectrum. So in this experiment, we are going to use the magnitude spectrum to compute the pulse rate. So let's start. In this is the code for the first part. So here we can see that this is our raw input data, and all of these are the variables that we're going to use in our code. Now let's move on to the code. So here you're going to compute the pulse rate of the given PPG sensor data using the DFT Magnitude Spectrum. The results are going to be compared with the ones obtained from autocorrelation function. So we set the sample size to 75. This is the moving average filter that we have discussed in our previous videos. And again, we set the number of sample points of MAF to 8. This for loop is used to compute the magnitude spectra of DFT. So here we have two variables, real and image. They are initially set to 0. And in this inner for loop, we traverse through the input array and consecutively add the values of this into real and the values of this into image. So as I said before, input of j denotes the value of input at the index j, and this here, this cos of 2 pi ij by n denotes the real value of the coefficients, and sine of 2 pi jn denotes the imaginary value of coefficient. So we multiply input with this cos value and consecutively add it in real, multiply the value of input with sine, and consecutively add it image variable, and we simultaneously add this to get the real and imaginary parts of x of k actually, and then to compute the magnitude of x of k we just do square root of real square plus imaginary square. In this way we are able to get the magnitude spectrum. Now we have to find the first peak value, and since we have a symmetric plot we will take the first value only. So we said k max is equal to 0 and k max value is equal to 0 initially, and these two will be used to compute the first peak value. So in this for loop, if the magnitude spectra at index I is greater than the kmax value, we put the value of kmax to I, and kmax value is equal to the value of the magnitude spectra at that index. So when this for loop ends, kmax will store the index at which we are getting the maximum value. And here we compute the frequency which presents the first peak, that is kmax into sampling frequency divided by 75, the sample size. And now we compute the pulse rate from the obtained frequency, which is just 60 into frequency. So we'll run this code and find out the pulse rate. We have got the pulse rate as 60 over here, and let's check the graph for this as well. We'll be able to see the twin max peaks that in the graph that denote the maximum frequency. I mean the peak frequency. Let's see the graph now. So here you can see that these two peaks are the ones that we get, and we take this first peak, the index of this first peak, to compute the pulse rate. Now let's run the same code. Let's check out what we get using the autocorrelation function. Though, so this autocorrelation function is the same one as we discussed in the previous video. Here we set the value of x array to the raw input PPG sensor data that we have just used before. And again, we set the sample size to 75. We have the moving average filter with a train of 8 sample points. There's mean subtraction going on when we compute the autocorrelation, as we have discussed before. We find the first negative zero crossing point, and then using that we find the value of L max that is the index at which the second maximum is occurring, and using that compute the time period, which is Lmax upon sampling frequency Fs, and using that we are able to compute the pulse rate, which is 60 upon time period. So let's check the pulse rate that we get from the autocorrelation function. So the pulse rate that we're getting from autocorrelation function is 71.43. The pulse rate that we got from DFT Magnitude Spectrum computation was 60. So let's move on to another implementation that I have done for the same conditions. But in this case, instead of that one big for loop which we use to directly compute the DFT into spectra, here I'm first computing the coefficients, and I'm making the coefficient matrix over here. So we're computing the coefficient matrix, and the real and imaginary parts are stored in two different matrices. So this here, the real coefficient matrix stores the real parts of the DFT coefficient, and the imaginary coefficient matrix stores the imaginary parts of the coefficient matrix. And here we just again multiply the input with the real coefficient and the input with the imaginary coefficient and get the magnitude spectrum. So everything else is the same as before, and let's check the pulse rate in this case. So the pulse rate again in this case is again 60, obviously, because everything else is just the same. So we know that in case of DFT computation, we are getting the pulse rate as 60, but when using autocorrelation, we are getting the pulse rate as 71.43. So let's take the same thing with MATLAB. So here this code is used. Is this code will compute the DFT Magnitude Spectrum and use that to obtain the pulse rate. And again, I have the autocorrelation function here. We're going to use that as well to compute the pulse rate. So everything else is just the same. We have the raw input data. We have the variable set up here, sample size, sample point, sample frequency. This here is the moving average filter. It's the same as I've discussed before. This here is the DFT Magnitude Spectrum computation. Is the exact same code in C that we did in Arduino. I've just adopted the MATLAB code, and the logic is still the same. So again, everything is just the same. We are finding out the KMax value, and we're using that to compute the pulse rate. So let's check out the plots of the raw PPG signal, the filtered PPG signal, and the magnitude spectra, and find the pulse rate. So I'm running this. So here we can see that this graph here is the raw PPG signal. The second graph here, it denotes the filtered PPG signal that we have got using MA filter, and the third graph over here is the magnitude spectra, and the pulse rate that we obtained in case is again 60. Now let's run the code for autocorrelation and relate it with the values that you got in the DFT code. Again, I'll just separate all these graphs so that you can see it clearly. Again, the first graph denotes the raw PPG signal, the second graph denotes the filtered PPG signal, and the third graph denotes the autocorrelation function. And the pulse rate that we obtained from the autocorrelation function is 68.1818. So we see that there's a very minute error between the pulse rates that we obtained from DFT and autocorrelation function. And this was it. This is what we did in the previous lab class. Thank you.